A cosmic tadpole is swimming through the void. This is the Tadpole Galaxy, a spectacular oddity known as UGC 10214, and its story is one of pure celestial chaos. Located an astonishing 420 million light-years away in the constellation Draco, this isn't a normal island universe. It is a uniquely distorted galaxy, forever marked by a single, catastrophic event that left it with a tail longer than our entire Milky Way. By the end of this journey, you will understand 30 of the strangest discoveries that make this object a cornerstone of modern astronomy. We will uncover what ripped this galaxy apart, why its colossal tail is birthing new worlds, and what ghostly forces are shaping its future. What does it feel like to witness a galactic accident frozen in time? This colossal tail is the galaxy's defining scar, a luminous wound stretching over 280,000 light-years across the emptiness of space. To put that into a human scale, if you could hold our own Milky Way in one hand, the tadpole's tail would stretch well beyond your fingertips. It is not a simple smear of light. Within that vast river of cosmic material, telescopes reveal a turbulent mix of hydrogen gas, dark lanes of dust, and brilliant blue knots that are actually massive clusters of newborn stars. This entire structure is a direct, visible consequence of a violent encounter, a galactic sideswipe that happened so recently in cosmic terms that the debris is still flying. We are looking at the aftermath of a car crash in space, but one where the vehicles are entire galaxies and the skid marks are 500,000 light-years long. The tail is essentially a roadmap of the disaster, showing us how material was violently stripped away and flung into the void, where it is now collapsing under its own gravity to form new solar systems. It is a stellar nursery born from pure chaos. This cosmic car crash has a clear suspect. The tadpole's bizarre shape is the direct result of a smaller, compact galaxy plowing straight through the heart of a larger, spiral galaxy like our own. This was not a slow, merging embrace. It was a high-speed hit and run, a violent sideswipe that happened hundreds of millions of years ago. Picture two galaxies on a catastrophic collision course. As the smaller intruder passed through the larger disk, its immense gravitational pull acted like a cosmic rake, tearing through the delicate structure. Stars and vast clouds of gas were not simply pushed aside, they were violently yanked out of their orbits. The gravitational forces were so extreme they stretched this material out into that incredible tail, much like pulling a piece of cosmic taffy into a long, thin strand. This event did not just distort the galaxy, it fundamentally rewired it, scattering its raw materials across the void. To understand this ancient violence, astronomers turned to digital time machines, sophisticated computer simulations that recreate the event. By inputting the laws of physics and the galaxy's current state, they can run the clock backwards and forwards. These simulations show that only a specific type of high-speed, penetrating collision could create a tail so long and so rich in star-forming material. The digital reconstruction matches the real telescope images with stunning accuracy, confirming we are witnessing the aftermath of a single, precise moment of interstellar chaos. That incredible tail is formally known as a tidal stream. In astronomy, this term describes a long, thin flow of stars and gas ripped from a galaxy by the gravitational pull of a neighbor. Think of our own ocean tides, where the moon's gravity pulls the water, creating a bulge. The process here is similar but scaled up to a catastrophic degree. Two galaxies pass close by, and their mutual gravity stretches them, pulling long arms of material out into space. While tidal features are common in the crowded universe, the Tadpole Stream is a record breaker, a galaxy-sized example of this phenomenon writ large across the cosmos. This makes it far more than just a pretty accident. For scientists, this stream is a dynamic laboratory. By studying its shape, density, and motion, astronomers can reverse engineer the collision that created it. They can calculate the speeds and angles involved, estimate the masses of the original galaxies, and understand how gravity redistributes an entire galaxy's worth of building blocks. This single stream teaches us universal rules about how galaxies interact, merge, and ultimately grow over billions of years. But the most stunning revelation is what is happening inside that river of debris. It is not just silent wreckage drifting in the dark. The Hubble Space Telescope's sharp eye has looked deep into the tail and found brilliant blue knots of light scattered along its length. Each of those blue knots is a massive cluster of newborn stars, some containing millions of young suns. The gas torn from the galaxy's disk became compressed and chaotic as it was flung outward, and in that turmoil, vast clouds collapsed under their own weight. This triggered a firestorm of star formation, turning a trail of destruction into a stellar nursery of epic proportions. We are literally watching new solar systems being born from the ashes of a galactic collision. The tadpole's tail is both a grave and a cradle, a paradox that shows how the universe often uses violence as a tool for creation. These brilliant blue knots of newborn stars face a profoundly uncertain future. Born from violence and cast adrift in the colossal tail, they are essentially orphaned stellar cities. Each cluster, packed with millions of young, hot, blue stars, shines with an intensity that betrays its chaotic origin. They did not form in the calm, rotating disk of a mature galaxy. Instead, they ignited inside the compressed and turbulent rivers of gas that were violently stripped away during the collision. This raises a fascinating cosmic mystery. What happens to these clusters now? They are currently moving along with the tidal stream, but their grip on that material is tenuous. One possibility is that gravity will eventually bind them to the main body of the Tadpole Galaxy. Over billions of years, they could settle into stable orbits, becoming a new generation of globular clusters, those ancient, dense balls of stars that orbit galaxies like cosmic satellites. Our own Milky Way is surrounded by over 150 such globular clusters, and their origins have long puzzled astronomers. The tadpole gives us a front-row seat to a potential answer, showing that some of these ancient clusters might have been born in the fiery chaos of galactic collisions, not in the quiet early universe. But there is another, lonelier fate. Some of these orphaned clusters may never find a permanent home. The gravitational pull of the tadpole might not be strong enough to reel them all back in, especially those formed farther out in the tail. These clusters could eventually break free, becoming true intergalactic wanderers. They would drift through the immense voids between galaxies, isolated island universes containing millions of stars but no galactic parent to call home. This discovery forces us to look at our own night sky differently. When we see a globular cluster like Omega Centauri, a dense swarm of stars orbiting the Milky Way, we might be looking at an ancient orphan, a survivor from a catastrophic galactic encounter that happened billions of years ago. The tadpole's tail is not just creating stars, it is seeding the future with celestial nomads. But the story of the collision is incomplete without the other driver. Look closely at the most famous Hubble image of the Tadpole Galaxy. Just above its distorted bluish core, you will see a small, compact, and distinctly yellowish smudge of light. That is not a background star. That is the intruder itself, the smaller galaxy that plowed through the tadpole hundreds of millions of years ago. It is still there, caught in a slow-motion cosmic dance, forever linked to the destruction it caused. This tiny yellow dot is a crucial piece of evidence. Its color tells a story of its own. Unlike the vibrant blue star forming regions it left in its wake, this galaxy glows with the golden light of ancient stars. The violent encounter likely stripped away most of its gas, the raw material for new stars, leaving behind an older, aging stellar population. By measuring its light and motion, astronomers can weigh it. They can calculate its mass, which in turn tells them about the force of the impact. The speed and angle of the collision can be reverse engineered from the positions of the two galaxies and the spectacular tail stretching between them. This intruder is a key witness, and its testimony helps scientists reconstruct the entire accident report from this ancient cosmic crash. So what becomes of this smaller galaxy now? The gravitational tether between the two is immense. One compelling possibility is that this is not a hit and run, but a hit and return. The intruder may have been slowed enough by the encounter that it lacks the velocity to truly escape. It could now be locked in a vast, elliptical orbit, destined to swing back and collide with the Tadpole Galaxy again and again over billions of years, until the two finally merge into a single, new type of galaxy. This would be a slow, drawn-out cosmic merger. Alternatively, it might have had just enough speed to make a clean getaway. It could be on a one-way trip out of the tadpole's gravitational grip, forever carrying the scars of the collision as it voyages alone through intergalactic space. Its fate hangs in the balance, a reminder that in the cosmos, even the most violent events are often just the first chapter in a much longer story. This violent collision has given us a unique opportunity to see the invisible. The chaotic dance of the Tadpole Galaxy is not just about the stars and gas we can photograph. It is also a window into the most mysterious substance in the universe, dark matter. We know dark matter exists because we can see its gravitational effects, but it emits no light, no radiation we can directly detect. It is a ghostly halo that surrounds every galaxy, providing the gravitational glue that holds them together. When two galaxies collide, however, something remarkable happens. The visible stars and gas interact and slow down due to friction, but the clouds of dark matter, which barely interact with anything, simply pass through each other. This separation creates a cosmic fingerprint. By meticulously tracking the motion of the tadpole's visible stars and gas, and comparing it to the overall gravitational pull needed to shape its long tail, astronomers can begin to map where the invisible dark matter must be. They are essentially weighing the galaxy by watching how its visible parts move, and the results suggest a significant mass we cannot see. This leads to a profound question about the collision itself. When the intruder galaxy plowed through, did it rip away some of the tadpole's dark matter halo along with the stars and gas, or did the ghostly halo remain mostly intact? Some studies suggest the dark matter, being so diffuse and non-interactive, may have been less affected by the collision than the visible material. The long tail might be mostly stars and gas, with the dark matter halo still enveloping the main galaxy body. Other models propose that dark matter could also be stretched into a vast, invisible stream, a shadow tail mirroring the luminous one we see. This remains an active and heated area of research. The answer is crucial because it tells us about the fundamental nature of dark matter itself. Is it sticky in a gravitational sense, or does it flow like a frictionless ghost? By studying the aftermath frozen in the tadpole, we are not just learning about one galaxy's accident. We are conducting a universe-scale experiment on the fabric of reality. The head of the Tadpole Galaxy spins with a secret. While its long tail captures all the attention, the main galactic body, that disturbed spiral disk, holds its own enigma locked within its motion. Astronomers can measure how a galaxy rotates by analyzing the light from its stars, seeing which side is moving toward us and which side is moving away. For a normal, undisturbed spiral like the Milky Way, this creates a predictable pattern, a smooth rotation curve where stars on the outer edges orbit at roughly the same speed as those closer in, a key signature of dark matter's influence. But the tadpole's rotation is anything but smooth. The violent collision that created its spectacular tail did not just rearrange its appearance, it fundamentally scrambled its internal clockwork. The orderly spin that likely existed before the impact has been thrown into disarray. Gas clouds and star clusters within the disk are now moving on chaotic, misaligned orbits, some perhaps even rotating in the opposite direction to the rest. This makes the galaxy's head a unique natural laboratory. By meticulously mapping these disturbed motions, scientists can trace how gravitational chaos rewires a galaxy's very engine over hundreds of millions of years. It is like studying a grand cosmic clock after it has been struck by a hammer, watching the gears slowly try to find a new rhythm. This scrambled rotation also impacts the galaxy's future shape. That orderly spiral structure requires a settled, uniform spin to maintain its iconic arms. The collision has robbed the tadpole of that stability, which is a key reason it looks so lopsided and disturbed today. The question now is whether this damage is permanent, or if, given enough cosmic time, the galaxy's own gravity can smooth out these wrinkles and restore some semblance of order. The answer lies in the next great disturbance waiting in the void. The violent collision did not drain the Tadpole Galaxy of its lifeblood. Deep within its chaotic swirls and along the length of its immense tail, radio telescopes have uncovered a hidden treasure, vast reservoirs of cold molecular gas. This is the raw, dark material from which stars are born, dense clouds of hydrogen and other molecules that exist in a frigid state, just waiting for a trigger to collapse into new suns. Using powerful instruments like the Atacama Large Millimeter Array, or ALMA, astronomers have mapped this invisible resource. What they found is both surprising and illuminating. Despite the galaxy's traumatic history, it remains incredibly gas-rich. These cold, dark clouds are not just present in the disturbed main disk, they are also abundant throughout the luminous tail, tracing the very path of destruction. This discovery solves a major puzzle. It explains the brilliant blue knots of star clusters we see. The collision did not merely scatter gas, it funneled and compressed it. As the intruder galaxy plowed through, it swept up immense rivers of this molecular material, squeezing it as it was flung outward. This compression is the ultimate cosmic trigger, turning quiet, cold clouds into raging stellar nurseries. The Tadpole is not a dying galaxy, it is a galaxy overflowing with potential, its trauma having unlocked a frenzied, galaxy-wide birth of new solar systems. Scattered like brilliant diamonds along a river of shadow, those blue knots in the tail are far more than simple groups of stars. They are cosmic powerhouses known as superstar clusters, and they represent some of the most extreme stellar nurseries we have ever observed. To understand their scale, think of a familiar star cluster like the Pleiades, the beautiful little dipper in our own night sky. That cluster contains a few hundred hot young stars. Now imagine a single object containing not hundreds, but hundreds of thousands, even millions, of young stars all packed into a region just a few dozen light years across. That is a superstar cluster. The gravitational energy in such a dense knot of stellar fire is almost unimaginable. These are not peaceful places. They are tempests of radiation and stellar winds where massive stars live fast, die young, and explode as supernova, constantly reshaping their own violent cradle. The tadpole's tail is strung with these phenomenal objects, turning a structure of destruction into a necklace of cosmic beacons. What makes them so special, and why do they captivate astronomers? They are a direct bridge to the ancient past. In our Milky Way, we see ancient globular clusters, dense balls of stars that formed over 12 billion years ago in the universe's chaotic infancy. For decades, their origin was a mystery. How did such dense, massive clusters form? The tadpole provides a stunning answer. Its superstar clusters are essentially newborn globular clusters. They are the modern-day equivalents of those ancient objects, giving us a front-row seat to a process we thought had ended eons ago. We are watching, in real cosmic time, how the universe's first magnificent star clusters were assembled. The violence of the galactic collision provided the perfect recipe, compressing unimaginable amounts of gas into tight, dense pockets where gravity could work its magic on an epic scale. Each superstar cluster in the tadpole's tail is a time capsule, not from the past, but from the very beginning, playing out right before our eyes. The very light from that tail carries a hidden message. When astronomers point their spectrographs at the tadpole's long stream, they are not just measuring brightness, they are reading a cosmic chemical fingerprint. By splitting the light into its constituent colors, they can identify the specific elements present in the gas and stars, a property known as metallicity. In astronomy, metals refer to any element heavier than hydrogen and helium, the primordial stuff of the Big Bang. These heavier elements, like carbon, oxygen, and iron, are forged only in the nuclear furnaces of stars and scattered by their explosive deaths. A region's metallicity is thus a history book, telling us how many generations of stars have lived and died there. The chemical analysis of the tail revealed a fascinating and unexpected story. It is not a uniform river. Instead, it shows a patchwork quilt of different metallicities. Some parts of the stream contain gas that is surprisingly pristine, with very low levels of heavier elements. This is primordial fuel, material that has remained largely untouched since the early universe, likely hauled out from the outer, less processed regions of the original galaxies. Interwoven with this ancient gas are pockets of highly enriched material, brimming with the heavy elements forged by many stellar generations. This enriched gas was clearly stolen from the bustling, star-filled disks of the colliding galaxies, where life and death cycles of stars had been enriching the environment for billions of years. This mix is a direct archaeological record. It allows scientists to trace individual clumps in the tail back to their neighborhoods of origin before the catastrophic collision. We can now look at a specific blue knot of stars and say, this cluster formed from gas that was once in the quiet galactic suburbs, while that one over there is built from the recycled remains of ancient stars from a bustling galactic downtown. The tail is not just a structure, it is a layered history, a fossilized snapshot of two entire galactic ecosystems being violently blended together. This cosmic collision reveals a deeper, universal hunger. The Tadpole Galaxy offers us a rare and vivid snapshot of a process astronomers call galactic cannibalism. It is the fundamental way our universe builds its largest structures, where bigger galaxies grow by consuming their smaller neighbors. While the dramatic tale makes this event look like a hit and run, the gravitational story is far from over. The intruder galaxy may have passed through, but it has not escaped. The two are now locked in a slow, inescapable dance, their fates woven together by gravity. This is not a finished meal, but a bite has been taken. We are witnessing the very first act of consumption, where a larger galaxy has stripped away a portion of a smaller one, digesting its gas and stars to fuel its own growth and spark new generations of suns. The long tail is the evidence of that first bite, material being drawn out and incorporated into the larger system. Over billions of years, the intruder will likely be pulled back, completing a drawn-out merger that will leave a single, larger, and probably elliptical-shaped galaxy in its place. This slow-motion feast makes the distant tadpole startlingly relevant to our own home. Our Milky Way is itself a cannibal, having absorbed smaller dwarf galaxies throughout its long history, and it is currently tearing apart and consuming the Sagittarius dwarf spheroidal galaxy. But the ultimate cosmic dinner date is already on the calendar. In roughly 4 to 5 billion years, the Milky Way will collide with the Andromeda Galaxy in an event that will reshape our entire night sky. The chaotic, distorted form of the Tadpole Galaxy is not some bizarre outlier, it is a preview. It shows us an early, violent stage of the very same process that will one day define our own galaxy's future. We are looking at a cosmic prophecy, a glimpse of the magnificent and terrifying chaos that awaits when our island universe is no longer alone. This chaotic tale is a cosmic laboratory unlike any other. It offers a front-row seat to star formation pushed to its absolute limits, a process far removed from the calm, rotating nurseries of a typical spiral galaxy. In a place like our own Milky Way, new stars are born in the dense, cold clouds that line its elegant spiral arms, a relatively orderly and slow-paced affair. But within the tadpole's immense stream, the rules are rewritten by violence. Here, star birth is not a gentle condensation, it is a firestorm ignited by shock waves. As the intruder galaxy tore through, it did not just pull gas outward, it sent titanic pressure waves rippling through those vast clouds. Think of it like a sonic boom on an unimaginable scale, a wall of force traveling through space and slamming into cold, quiet reservoirs of hydrogen. These shockwaves violently compress the gas, squeezing it in an instant to densities that would take millions of years to achieve through gravity alone. This sudden, extreme pressure is the ultimate trigger, forcing countless pockets of gas to collapse all at once in a frenzied burst of creation. This is star formation as a catastrophic event, a stellar baby boom born from pure bedlam. By studying the brilliant blue knots scattered along the tail, astronomers are not just looking at pretty lights, they are decoding the physics of chaos itself. They can measure the speeds of these shock waves, calculate the densities they create, and observe the types of stars that form in such a turbulent nursery. This teaches us that the universe has more than one recipe for building solar systems. It shows that some of the most prolific star-forming events in cosmic history, perhaps those in the early, crowded universe, were likely driven by this very same mechanism, colossal collisions sending shockwaves through pristine gas to light up the darkness with billions of new suns. The tadpole's tail is a time machine, showing us how the most violent chapters of the universe's story are also its most creative. But the fireworks in this cosmic nursery are not just visible light. Peering into the tadpole with X-ray eyes reveals a hidden layer of violence. Space observatories like Chandra have detected bright, pinpoint sources of high-energy X-rays scattered across the galaxy and its tail. These are not gentle glows, they are cosmic screamers, signals of the most extreme environments imaginable. Each of these brilliant X-ray dots likely tells a story of stellar drama. Many are binary star systems locked in a deadly embrace, where a dense, compact object like a neutron star or a black hole is actively feeding. In these systems, the immense gravity of the dead star pulls gas from its living companion, spiraling that material in at nearly the speed of light. As this stolen gas crashes onto the surface of the neutron star or swirls into the black hole's accretion disk, it is heated to millions of degrees, erupting in a torrent of X-rays. Other sources could be the superheated remnants of recent supernova explosions, vast bubbles of gas still seething from the blast. Their very presence and distribution are a map of aftermath. They show us in stark relief where the most massive stars from that collision-induced baby boom have already lived their short, furious lives and met their explosive ends. The X-rays paint a picture of a galaxy not just recovering from one ancient collision, but crackling with the ongoing, high-energy echoes of the new universe it created. Deep within the galaxy's chaotic heart lies another mystery. While the spectacular tail draws our eyes outward, some telescopic studies have peered into the tadpole's very center and found something unusual. The bright, compact core of the galaxy might not be a single, unified object. Instead, there are tantalizing hints of a double structure, two distinct knots of intense light and energy nestled close together at the galactic center. This discovery opens a door to a staggering possibility. One of these bright cores likely belongs to the Tadpole Galaxy's own supermassive black hole, the immense gravitational anchor common to most large galaxies. The other could be the lingering heart of the intruder. When that smaller galaxy plunged through, it did not leave its central monster behind. It brought its own supermassive black hole along for the ride, and that dark behemoth may now be orbiting within the tadpole's newly blended core. We could be witnessing the early stages of an event of almost unimaginable scale, two supermassive black holes, each weighing millions or even billions of times the mass of our Sun, beginning a slow gravitational dance. This dance is not a quick step, it is a waltz that will last for hundreds of millions of years. Initially, the two black holes will circle each other at a distance, their immense gravity shaping the orbits of the stars around them. As they lose energy by flinging those stars away, they will spiral closer and closer. This leads to a profound question for astronomers. If they are there, can we see them? Directly imaging such a close pair is currently beyond our technology, but we can search for indirect signatures. Scientists look for telltale patterns in the motion of stars at the galaxy's center, or for specific flickers in the light that suggest two separate engines of activity are at work. Confirming this double nucleus would transform our understanding of the collision. It would mean we are not just seeing the aftermath of stars and gas being scattered, but the far more consequential merger of two galactic hearts. This slow cosmic dance has an inevitable, violent finale. Eventually, the two black holes will get so close that no star can separate them. They will plunge together, merging into a single, even more massive black hole. That final collision will shake the fabric of spacetime itself, rippling out gravitational waves, distortions in reality that we can now detect with observatories like LIGO. The Tadpole Galaxy might one day, in the far distant future, broadcast its final act across the entire universe. Even the silent void of that colossal tail is not truly empty. It is threaded with invisible lines of force, a ghostly magnetic field stretched thin across hundreds of thousands of light years. This is one of the tadpole's most subtle and esoteric discoveries, revealed not by optical light, but by listening to the whisper of radio waves. When astronomers train their most sensitive radio telescopes on the stream, they can measure a property called polarization, the specific orientation of the radio waves as they travel through space. The data suggests a remarkable order amidst the chaos. The radio waves are aligned, telling scientists that the tail itself possesses a large-scale magnetic field, one that has been stretched and combed straight, running like cosmic fibers along the length of the stream. This magnetic field is a fossil imprint of the collision. Before the disaster, both galaxies likely had their own tangled magnetic fields woven through their disks. When the intruder plowed through, it did not just pull on stars and gas, it pulled on these invisible lines of force as well, yanking them out into the void and aligning them with the direction of the material flow. Think of it like pulling a handful of chaotic, curled hairs straight, aligning them into a single, smooth strand. This discovery transforms our understanding of the tail from a simple river of debris into a structured, dynamic entity. Magnetic fields are not just cosmic decoration. They play a crucial, active role in how the universe builds things. Within a cloud of gas, magnetic forces can provide support against gravity, slowing or even preventing collapse. But they can also channel material, guiding flows and concentrating gas into denser filaments. In the tadpole's tail, this stretched magnetic field likely acted as a cosmic guide wire. As the shocked and compressed gas began to collapse to form those brilliant blue star clusters, the magnetic field would have influenced how the material fell together, perhaps helping to funnel gas along specific paths and increasing the efficiency of star birth. Measuring such a faint, ordered field across such a vast distance is a triumph of modern astrophysics. It requires combining data from multiple radio observatories and painstakingly filtering out interference from our own galaxy and other sources. It is like trying to hear a single, soft violin note played in a hurricane. This difficult measurement does more than just add another fact to the list. It reminds us that to truly understand a cosmic event, we must see all its layers, not just the blazing light of newborn stars, but the silent, sculpting force of magnetism that helped shape them. That faint, stretched magnetic field is just one piece of a larger cosmic puzzle. To truly grasp the tadpole story, we need to know exactly how far away this drama is unfolding. This brings us to one of its most practical and profound contributions to astronomy, its role as a cosmic measuring stick. The Tadpole Galaxy has been used as a standard candle, a fundamental tool for mapping the vast scales of the universe. In astronomy, a standard candle is any object with a known, consistent intrinsic brightness. By comparing how bright that object appears from Earth to how bright we know it actually is, astronomers can calculate its distance with remarkable precision. It is like seeing a 100-watt light bulb in the distance. If you know it is a 100-watt bulb, you can judge how far away it is by how dim it looks. The challenge, of course, is finding a reliable cosmic light bulb. For the tadpole, astronomers found their perfect candle flickering within its chaotic embrace, a specific type of pulsating star called a Cepheid variable. These are aging, giant stars that rhythmically swell and shrink, causing their brightness to pulse with a clockwork regularity. The key discovery made by astronomer Henrietta Leavitt over a century ago is that the rate of this pulsing is directly tied to the star's true brightness. A Cepheid that pulses slowly is inherently very bright, while one that pulses quickly is fainter. By finding Cepheids in the Tadpole Galaxy and meticulously timing their pulses, astronomers could determine their true wattage. Then, by measuring how dim they appeared through the telescope, they could perform the cosmic math to pinpoint the galaxy's distance at 420 million light-years. This measurement is not just a number in a catalogue, it is a critical rung on the cosmic distance ladder, the interconnected series of methods we use to measure the scale of the cosmos. Cepheids in nearby galaxies calibrate other, brighter standard candles like supernova, which can then be seen in galaxies billions of light-years away. Each step builds on the last, and a precise distance to a galaxy like the tadpole strengthens the entire structure. This is why it matters for our biggest questions. The cosmic distance ladder is the very tool we use to measure the expansion rate of the universe, a number called the Hubble constant. Discrepancies in this rate are one of the greatest mysteries in modern cosmology, hinting at unknown physics or new cosmic ingredients. By serving as a well-measured milepost, the Tadpole Galaxy helps tighten those measurements, turning its chaotic light into a ruler for the cosmos. Beyond the brilliant river of the main tail, the collision's true scale only emerges in the deepest shadows. The most sensitive telescopes have peeled back the glare to reveal something astonishing: faint, gossamer threads of starlight stretching even farther into the void. These are not the dense, star-forming rivers we see in the famous image. They are the ghosts of the collision, ethereal streams of individual stars that were gravitationally flung to the outermost edges during the chaotic encounter. While the bright tail contains compressed gas and bustling star clusters, these ultra-faint streams are made of stars alone, ancient suns that were ripped from their homes and now drift in lonely, stretched-out orbits. Mapping them is like trying to see a single candle flame from across an ocean at night. It pushes our most advanced observatories to their absolute limits, requiring hours upon hours of exposure time and sophisticated computer processing to filter the faint stellar signal from the overwhelming glow of Earth's own atmosphere and the background light of the universe. But the effort reveals a hidden truth. The violence of the impact reached much farther than we initially thought. The gravitational shockwave did not just pull out a neat tail, it sent a spray of stars flying in all directions like water droplets shaken from a wet dog. These faint streams are the evidence of that spray, tracing the most energetic trajectories of the disaster. For scientists, they are a supreme test of our models of gravitational dynamics. Computer simulations of the collision can now be checked against this faint, real-world evidence. Do the predicted paths of these orphan stars match where we actually see them? The answer tells us if we truly understand the precise speeds, angles, and gravitational forces involved in that ancient moment of chaos. Each faint stream is a delicate signature, a cosmic fingerprint left by gravity itself, and by reading it, we refine our understanding of how the universe moves its pieces in the aftermath of catastrophe. This beautiful mess of a galaxy breaks all our cosmic filing systems. For decades, astronomers have used the elegant Hubble sequence to categorize galaxies, a simple tuning fork diagram with spirals on one branch and smooth, football-shaped ellipticals on the other. The Tadpole Galaxy laughs at this neat arrangement. It is the textbook definition of a peculiar galaxy, a one-of-a-kind cosmic oddball that cannot be squeezed into any standard box. Its spiral arms are mangled and lopsided, its core is disturbed, and its defining feature, that colossal tail, simply has no place in the traditional scheme. This is not a failure of our charts, but a revelation. The tadpole screams that galaxy evolution is not a tidy, linear process. It is a violent, chaotic, and deeply messy affair, shaped by random collisions and brutal gravitational encounters that leave permanent scars. For every serene spiral like our Milky Way, there are countless others bearing the wounds of their history. This peculiarity forces a profound shift in perspective. Our own beautifully ordered galaxy, with its symmetrical arms spinning in calm majesty, is likely the cosmic exception, not the rule. In the crowded, chaotic early universe, galaxies were packed closer together, and titanic collisions like the one that forged the tadpole were commonplace. Most galaxies in that distant epoch probably looked far more like this distorted tadpole than like our neat spiral home. We are the odd ones out, the rare product of a long, quiet period of isolated evolution. The tadpole, in all its glorious imperfection, is a window into the universe's true, untamed nature, a reminder that the cosmos prefers beautiful chaos over neat classification. But the visible light and X-rays are not the whole story. To see the true warmth of this cosmic nursery, you must look in a different light, the gentle, pervasive glow of the infrared. When the Spitzer Space Telescope turned its infrared eyes toward the tadpole, it revealed a hidden layer of the galaxy, one that optical images could never capture. The entire system, from its chaotic head to the farthest reaches of its tail, was bathed in a tremendous, soft glow. This is not the light of stars themselves, but the thermal signature of warm cosmic dust. Tiny grains of silicate and carbon, smaller than a particle of smoke, are scattered everywhere, and they are being heated by the very stars they help to create. This infrared glow is a direct measure of the galaxy's frantic reproductive energy. Every one of those brilliant blue superstar clusters is pouring out intense ultraviolet radiation, which is then absorbed by the surrounding dust clouds. The dust grains warm up from just a few degrees above absolute zero to dozens or even hundreds of degrees, and re-radiate that energy as the infrared light that Spitzer detected. This transforms our understanding of the tadpole's activity. An optical telescope sees the dazzling end result, the clusters of hot, young stars. But the infrared view shows us the bustling, dusty factories that are still at work, the hidden cradles where new stars are currently being forged behind curtains of obscuring material. It reveals structures completely invisible in the famous Hubble image, dense lanes and knots of warm dust that trace the most active, ongoing sites of stellar birth. This complete picture tells us the star formation frenzy is even more widespread and intense than we first thought. The infrared glow is the comforting heat of a cosmic incubator, proving that the tadpole's creative chaos is still very much alive. The tadpole's unique shape makes it a perfect cosmic puzzle for astrophysicists to solve. This galaxy is a premier testbed for the most advanced supercomputer simulations of galactic collisions. Scientists don't just create models of generic crashes, they attempt to recreate the tadpole itself with all its specific, bizarre details. They input the laws of physics as we understand them, set initial conditions for two hypothetical galaxies, and then let the digital universe run. The goal is not just to make a tail appear, but to produce a virtual galaxy that matches the Hubble image in every particular, the exact length and curvature of the stream, the distribution of those blue star clusters, and the disturbed rotation of the core. This is an incredibly precise challenge, To succeed, the simulation must perfectly account for the complex dance of gravity, the hydrodynamics of colliding gas clouds, the recipes for triggering star formation, and even the feedback from supernova explosions. When a simulation fails to match reality, it is not a disappointment, it is a breakthrough. It tells the scientists that something is missing from their equations, perhaps a misunderstanding about how dark matter behaves during a collision, or an underestimation of how stellar winds from newborn stars push back on surrounding gas. Each mismatch is a clue pointing toward a deeper physical truth. The most successful simulations are breathtaking, producing side-by-side comparisons where the computer-generated image is nearly indistinguishable from the real cosmic photograph. This process does more than explain one galaxy. It stress-tests our entire understanding of how the universe works on the grandest scales. The tadpole in its frozen chaos is the ultimate final exam for our theories of cosmic evolution. The violence that sculpted this galaxy was not a slow-motion crush, but a high-speed bullet. Astronomers have pieced together the forensics of the collision and calculated the staggering speed of the intruder galaxy. By analyzing the immense length of the tail and the current positions of the two galaxies, they estimate the smaller galaxy was moving at several hundred kilometers per second when it plowed through the tadpole's heart. To grasp that scale, picture this: a spacecraft moving at that velocity could travel from the Earth to the Moon in under 20 minutes. This incredible speed was the defining factor in the disaster's outcome. If the collision had been slower, gravity would have had time to act like a cosmic glue. The two galaxies would have quickly tangled together, merging into a single, messy blob in a relatively short cosmic time. Instead, the intruder was moving so fast it acted more like a cannonball. It punched straight through the disk, delivering a single, catastrophic gravitational yank. Its immense pull stretched the tadpole stars and gas in one sharp, violent tug. Then the intruder kept right on going, leaving the debris to slowly unfold into that spectacularly long tail over hundreds of millions of years. This was not a union, it was a hit and run of truly epic proportions. The speed created the perfect conditions for a tidal stream of such pristine length and clarity, making the tadpole a textbook example of a high-velocity galactic sideswipe frozen in time. This selective stripping of stars paints a surprising portrait of the collision's violence. While the tail is brimming with hot, blue newborns, detailed surveys have noticed a curious absence. Where are the older, red giant stars? In a typical galactic mix, you would expect to find these swollen, aging suns scattered among the younger populations, the inevitable result of stellar evolution. Their apparent scarcity in the long stream is a subtle but critical clue. It tells us the tidal forces were not a blunt instrument that ripped everything out equally. They were precise, almost surgical in their destruction. The collision primarily stripped material from the galaxy's thin, gas-rich disk, where younger stars reside, and from the vast reservoirs of cold molecular gas between them. The older stellar population, which often forms a more diffuse, spherical halo around a galaxy, appears to have been less affected. This makes gravitational sense. The dense, rotating disk is more vulnerable to a gravitational yank. A passing intruder can get a firm grip on that orderly structure and pull it apart. The halo, however, is a much looser, three-dimensional cloud of ancient stars. The same gravitational pull that stretches the disk into a tight stream might simply cause the halo stars to wobble in their orbits, not eject them entirely. This selective theft reveals the anatomy of the disaster. We are not seeing a galaxy completely disemboweled, but rather skinned, with its outer layers of gas and young stars flayed away while its deeper, older skeletal structure remained more or less in place. The tail is not a random sample of the entire galaxy. It is a specific component, a biopsy of the disk taken during a moment of extreme trauma. Those brilliant clusters in the tail might be destined for a future far grander than mere ornaments. As these superstar clusters age and their most massive stars explode, they will release enriched gas back into their surroundings, a process that could allow them to capture more material over billions of years. If a cluster is massive enough, and if it can gravitationally bind a halo of dark matter around itself, a distinct possibility given the collision's chaos, it could evolve into something entirely new. It might transform from a cluster into a small, independent dwarf galaxy. This means the tadpole could be caught in the very act of cosmic reproduction, using the debris of its own destruction to spawn a family of satellite galaxies. We see this family structure all around us. Our own Milky Way is orbited by dozens of dwarf galaxies like the Large and Small Magellanic Clouds. For a long time, their origin was a puzzle. Did they form independently and were later captured, or were they built from the ground up? The tadpole offers a compelling third option. Some of these dwarf satellites might not be primordial building blocks at all, but rather the mature descendants of tidal debris, orphan star clusters that grew up and gained their independence. The long tail is a stellar assembly line, and its products might one day become miniature galaxies in their own right, forever orbiting the larger structure that created them. This turns a single collision into an engine for galactic legacy, where destruction directly seeds new, enduring celestial societies. 420 million years is more than just a distance, it is a journey back in time. The light now reaching our telescopes from the Tadpole Galaxy began its voyage when Earth was a very different world, a place where primitive amphibians were just beginning to crawl onto land. This immense time lag is not a barrier to understanding, it is the ultimate gift. Because light travels at a finite speed, we never see the cosmos as it is, only as it was. The chaotic, distorted shape of the tadpole is not a snapshot of the present, but a fossilized portrait of a younger, more violent universe. This makes it a priceless time capsule. The era it represents, hundreds of millions of years in the past, was still a time of frequent and dramatic galactic encounters. The universe was denser then, with galaxies packed closer together like a bustling cosmic city, making collisions and mergers a regular feature of existence. Today, as the universe expands and galaxies drift farther apart, such spectacular crashes have become rarer events. By studying the tadpole in exquisite detail, we are not just analyzing one peculiar galaxy. We are gaining a local, close-up view of the chaotic construction phase that built most of the grand galaxies we see today. It is a living relic from the universe's more tumultuous adolescence, a nearby example of processes that were once commonplace across the cosmos. This transforms it from an oddity into a vital reference point. When our most powerful telescopes peer to the very edge of the observable universe, they capture faint, blurry smudges of light from galaxies that existed over 12 billion years ago. Those distant objects are often too faint and small to reveal their intricate structures, but by understanding the mechanics, the physics, and the outcomes displayed so clearly in the tadpole, astronomers can interpret those ancient, fuzzy blobs. They can say with greater confidence that a particular distant galaxy's light profile matches what we would expect from a colossal collision similar to the one that created the tadpole's tail. This nearby chaos becomes the key that unlocks the distant past. The Tadpole Galaxy is a Rosetta Stone, translating the violent grammar of the early universe into a language we can understand today. Even the radio waves from this region tell a story of hidden things. Catalogued across the tadpole's chaotic field are dozens of unidentified point sources, bright pinpricks of radio emission with no obvious counterpart in optical or infrared light. They are cosmic ghost signals without a face. In the crowded stellar backdrop of the collision, these mysterious sources could be almost anything. Some are likely distant quasars, the blazing cores of galaxies billions of light years behind the tadpole, their visible light dimmed by dust but their powerful radio jets still punching through. Others might be rare and exotic stellar remnants within the tadpole itself, like microquasars, where a stellar mass black hole is actively feeding and shooting out radio-emitting jets. There is even the possibility that some of these radio whispers come from objects we have yet to properly classify, transient events or oddities that only reveal themselves in this specific slice of the electromagnetic spectrum. This transforms the tadpole from a single object of study into a rich hunting ground. Astronomers use its luminous chaos as a sort of cosmic fishing net. By staring deeply at this one patch of sky with radio telescopes, they catch all sorts of strange phenomena that would be harder to isolate in a quieter, emptier region of space. Each unidentified source is a small mystery, a reminder that for all we have learned about this spectacular collision, the universe continues to hide secrets in plain sight, broadcasting them on frequencies just beyond the light our eyes can see. The brilliant chaos of those superstar clusters contains a self-destruct mechanism. Within each dense blue knot, the most massive stars are living fast and dying young, and their spectacular deaths are not just an end, they are a powerful regulatory force for the entire galaxy. This process is known as astrophysical feedback, and the tadpole's tail is a perfect laboratory to watch it unfold on a cosmic scale. Feedback is the universe's way of balancing its own creative frenzy. When a cluster of massive stars ignites, it does more than just shine. These titans pour out intense ultraviolet radiation and powerful stellar winds, streams of charged particles moving at millions of kilometers per hour. This energy carves into the surrounding gas clouds, heating them, ionizing them, and literally pushing them away. Then, when the most massive stars reach the end of their brief lives, they explode as supernova. A single supernova can outshine an entire galaxy for weeks, and its shockwave injects a staggering amount of energy and newly forged heavy elements back into the surrounding space. This double punch of winds and explosions acts like a cosmic broom, sweeping clean the stellar nursery. It disperses the very gas clouds that gave the stars birth, preventing that same gas from collapsing to form the next generation. In a sense, star formation sows the seeds of its own shutdown. The tadpole allows us to study this self-regulating thermostat in an extreme, isolated environment. The tail is essentially a chain of isolated star-forming factories, each at a different stage of this cycle. By comparing clusters, astronomers can see which ones are still shrouded in dense gas, which ones have begun to blow clear bubbles around themselves, and which have already dispersed their raw materials entirely. This teaches us a fundamental rule of cosmic ecology: no stellar baby boom can last forever. The very violence of creation ensures it will eventually run out of fuel. This feedback loop is crucial for understanding not just the tadpole, but the evolution of all galaxies. It explains why galaxies don't convert all their gas into stars in one frantic burst. It spreads star formation out over billions of years, allowing for the gradual build-up of elements necessary for planets and ultimately life. The tadpole's tail, in all its fiery glory, is showing us the beautiful, brutal physics that prevents the universe from burning itself out too quickly. The immense mass of the Tadpole Galaxy warps the very space around it. This distortion creates a natural cosmic telescope, a phenomenon predicted by Einstein where gravity bends the path of light. The galaxy's vast collection of stars, gas, and its enormous halo of dark matter combine to form a powerful gravitational lens. While its chaotic shape does not produce the perfect ring-like arcs seen around some massive galaxy clusters, it is a prime candidate for weaker, more subtle lensing effects. Astronomers meticulously scan its outskirts, searching for telltale smears or stretched shapes of background light. The goal is to find galaxies so far behind the tadpole that their light has been bent and amplified by its gravitational field. This is a cosmic game of hide and seek where the tadpole itself becomes the magnifying glass. A successful detection would be a monumental discovery. It would allow us to peer at galaxies from the universe's first chapters, objects so faint and distant they are otherwise completely invisible to our telescopes. The lensed light would be a ghostly echo traveling for over 12 billion years, only to have its final path curved by this chaotic modern-day collision. Finding such an arc would do more than reveal an ancient galaxy. It would precisely weigh the tadpole's total mass, including every ounce of its elusive dark matter, by measuring how severely it bends the fabric of reality. This single, distorted smear of background light could connect two cosmic eras, linking a recent act of destruction with a glimpse of the universe's birth. Even the color of the light tells a story of sequence. Look closely at the tadpole's tail, and you will notice it is not a uniform river of blue. Instead, it possesses a subtle but significant color gradient, a shift in hue from one end to the other. The regions of the tail closest to the galaxy's disturbed head glow with a vibrant electric blue. This is the signature of youth, the intense light from massive, hot, newborn stars in those superclusters. But as your eye travels farther out along the stream toward the fainter, more distant tip, the color begins to change. It shifts toward a redder, more subdued tone. This is not a random artistic effect. It is a chronological map, a cosmic timeline painted in light. The color gradient acts like the rings of a tree, recording the sequence of events as the tale was born. Here is how it works. When the intruder galaxy first plowed through, it grabbed the nearest material first, yanking it out in the initial violent tug. This gas, ripped from the inner regions, was flung out but remained relatively close to the main galactic body. It was the first to be compressed, the first to collapse under its own gravity, and therefore the first to ignite into brilliant blue star clusters. Think of it as the first wave of debris in an explosion, launched with tremendous force but settling closest to the blast site. As the collision continued, the gravitational pull stretched out farther, hauling material from the galaxy's outer disk. This gas had a longer journey. It took more time to travel out to the farthest reaches of the growing tail, and more time for the shockwaves to ripple through it and trigger collapse. By the time these distant regions finally coalesced into stars, the earlier, inner clusters had already been shining for millions of years. Some of their most massive stars might have even lived and died already, enriching the local environment with the dust from their explosions. This dust can redden the light from more distant stars, much like a sunset appears redder because sunlight passes through more of Earth's atmosphere. So the redder hue at the tail's tip could signify two things. It could indicate slightly older stellar populations, stars that formed later in the sequence and have had more time to age and cool. Or it could point to regions still shrouded in the dusty remnants of that first wave of star formation, their light filtered and reddened as it travels to us. This elegant color gradient is a direct readout of the disaster's unfolding physics. It confirms that the tail did not form all at once, but in a wave, a stellar chain reaction propagating outward from the point of impact. By simply measuring the color of the light, astronomers can reconstruct the order of creation, turning a single, frozen snapshot into a moving picture of cosmic evolution. The most violent X-ray sources in the tail defy simple explanation. These are not the typical screams of a stellar black hole feeding, they are cosmic roars. Astronomers classify them as ultra-luminous X-ray sources, or ULCs, and each one outshines the entire X-ray output of a million suns. Their staggering brightness presents a fundamental puzzle. According to our standard physics, a normal stellar mass black hole, the remnant of a single collapsed star, has a maximum brightness it can achieve as it feeds, a limit called the Eddington luminosity. Push past that limit, and the radiation pressure from the infalling material becomes so intense it should blow away the very gas cloud that is feeding it, like a fire hose blasting away its own water supply. Yet ULXs blaze far beyond this theoretical ceiling. They are breaking the rules, and the tadpole's tail is hosting several of them. This forces a thrilling possibility. One leading theory is that these are not ordinary black holes at all, but intermediate mass black holes, monsters with the mass of hundreds or even thousands of suns. These would be the missing link between the stellar mass black holes born from dying stars and the supermassive giants that lurk in galactic cores. Their stronger gravity could, in theory, allow them to swallow more material at once, generating the incredible X-ray fury we detect. Another compelling idea is that we are seeing stellar black holes in a state of extreme and messy gluttony. Perhaps they are feeding not in a neat, steady disk, but in a chaotic, dense torrent of gas where the usual rules break down, allowing them to binge far beyond their supposed limits. The collision created the perfect cafeteria for such monsters. By ripping out vast amounts of gas and compressing it into the tail, it provided an unprecedented buffet of raw material. Then, within the superstar clusters, the dense environment could have fostered the runaway collisions of massive stars needed to forge a middleweight black hole, or it could have funneled insane amounts of fuel onto an existing one. Each ULX is a beacon pointing to a rare and extreme gravitational engine, one whose very existence challenges our understanding of how black holes grow and feed. Their presence in the debris stream is a direct signature of the collision's power, proving it did not just make stars, it forged the rarest and most voracious beasts in the cosmic deep. The ultimate fate of this cosmic tadpole is a story still being written in the slow ink of gravity. Over the next several billion years, the galaxy's colossal tail will not simply hang in space, it will evolve, dictated by the same forces that created it. One inevitable change is a gradual dimming of its brilliant blue fire. The frenzied star formation within the tail cannot last forever, as the supernova feedback from those massive clusters will eventually blow away or consume the remaining gas. The blue knots will fade, their hottest stars dying off, leaving behind a long, faint river of older, redder suns and the glowing remnants of stellar explosions. This ghostly stream will become a testament to a burst of creativity that has passed, a fossil of the collision slowly cooling in the dark. But the tail's structure itself faces two possible destinies, hinging on a single question: what is the intruder galaxy doing now? If the smaller galaxy retained enough speed to truly escape, then the tail's material is essentially unbound debris on a one-way trip into the void. In this scenario, the tail will slowly drift apart, its stars dispersing over eons into a diffuse cloud around the main galaxy, a barely visible halo of cosmic memory. The tadpole would remain a distorted spiral, forever bearing the scar of its encounter, but ultimately moving on alone. The far more dramatic future, however, is a return. The intruder may be on a vast, elliptical orbit, destined to swing back. If this is the case, then the current spectacle is merely the opening act. In a few billion years, the smaller galaxy could come crashing back into the tadpole's disturbed heart. This second collision would not be a clean sideswipe, but a slower, messier merger. The two galaxies would tango, their gravity thoroughly intertwining, their structures completely destroyed. The beautiful, lopsided spiral and its long tail would be churned into a new form, likely a featureless elliptical galaxy, a smooth swarm of ancient stars with no disk, no arms, and no more frantic star birth. The tail itself would be pulled back in, its stars and clusters either absorbed into the new galactic core or scattered into a vast spherical halo. This grand merger would be the final chapter, erasing the tadpole's distinctive shape forever, but creating a larger, more massive galaxy in its place. Its story would end not with a fade, but with a transformative crash, so which future awaits, our telescopes cannot yet give a definitive answer, as measuring the precise trajectory of the faint intruder across such immense distances is a monumental challenge. This uncertainty is the final gift of the Tadpole Galaxy. It reminds us that the cosmos is not a static museum, but a living, changing arena. We are not looking at a finished painting, but at a single, breathtaking frame in a film that is still playing. The tadpole's chaos is not its end, it is simply its current state, a dynamic system whose next act, whether a quiet fade or a violent reunion, is already written in the silent mathematics of gravity, waiting eons to unfold. From a chaotic splash of light to a cosmic masterclass, the Tadpole Galaxy has revealed itself as one of the universe's most profound teachers. This journey through 30 strange discoveries has shown us far more than a simple accident frozen in time. We have witnessed a high-speed collision that stretched an entire galaxy, turning destruction into a stellar assembly line where superstar clusters ignite. We have seen how it serves as a scale to weigh dark matter, a clock to measure cosmic expansion, and a fossil revealing the violent adolescence of most galaxies. It demonstrates the cannibalistic nature of galactic growth, the self-regulating feedback of star formation, and the potential birth of dwarf galaxies from tidal debris. Each oddity, from its scrambled rotation and magnetic fossil to its ultraluminous X-ray sources and color-coded timeline, is a piece of a grander puzzle. The tadpole is not merely a peculiar shape in the void. It is a dynamic laboratory, proving that the universe builds its greatest structures through chaos, using violence as a tool for breathtaking creation. It reminds us that our own orderly Milky Way is the exception in a cosmos ruled by beautiful, colliding chaos. So, which of these 30 discoveries captured your imagination the most? Was it the orphan star clusters destined to wander the void, the hidden dance of twin supermassive black holes, or the simple, profound fact that we are looking hundreds of millions of years into the past? Let us know in the comments below. If unraveling cosmic mysteries like this fuels your curiosity, be sure to subscribe for more journeys to the edges of space and time. And tonight, if you have a moment, look up the Tadpole Galaxy online. Find that iconic Hubble image and remember, you are not just looking at a pretty picture. You are witnessing a masterclass in the forces that shape everything.